material, this device which we make from semiconductor has that special property that it can only conduct current in one direction. So there is a practical application for this device, and we call it diode. And that is what we want to see here. Let me see, where is it? Goodness. Seem to have lost what? Let me just go to it. Yeah, it is here. The semiconductor diode is what is a semiconductor diode? Is a crystalline piece of semiconductor material with a PN junction. So when we connect it to an external source of voltage, we can make use of it. And the symbol for this device, which we call diode, is this one. Look at this symbol. It is like an arrow with a line here, and one side of the device we call anode, and it is marked positive. The other side we call cathode, and it is marked negative. So what I'm showing here, what I am pointing at, of course, you can see what I'm pointing at?
Yeah.
Yeah, this is the symbol for a diode, and the diode is meant from a semiconductor material, which has the PN junction. Now, if you go to our labs, you ask for a diode, you'll be given a small device which looks like this. It's cylindrical in nature, and one side there is a band. That side with a band shows which side is negative. And so the negative is here. So when you are connecting a circuit involving a diode, you must forward bias it. So you must connect the terminals correctly. The negative you connect it to negative, the positive you connect to positive of the power supply. So here we are showing the symbol, and we are showing the real device, how it looks like: a small cylindrical device with a band, a single band, not many. If you see a device with many bands, that is something different, which we call resistor. So at least you are able to appreciate when you see a circuit like this. When you see this circuit, we have the symbol of diode, so here we have connected two diodes, and here we have connected 4 diodes. So before we come to this, I just wanted to show you a circuit diagram showing diodes in the circuit. So let's take ourselves back. We have seen the symbol of a diode, how a real diode looks like. And so in a circuit diagram, we use the symbol. Then are we able to determine the current passing through a diode? We can do that using what we call Shockley equation. This equation, we call it Shockley. I think here it has not been named. So it is telling us the current through a diode is given by this equation, and we have defined the symbols which are used. If you see here, let me magnify it a bit. If you see this equation, we have ID. ID is the diode. Current, IS, is what we call reverse saturation current, the small current which flows when the diode is reversed. Then E we call it exponent, and it is raised to power VA divided by eta. This letter which looks like N, we call it eta. VT is what we called previously, we called it thermal voltage. So all the symbols are defined here, and the value of eta is between 1 and 2. VA is applied voltage, which we said is also known as biasing voltage. Anybody with a question? Now this equation now, we can also derive it, but I think at your level we may not go to that, but we are able to use it. Given this equation, you can use it, or if you are asked to use it, you can use. Now look, there's an example there. Akod, can you read that example?
Determine the current in a PN junction at temperature 300 Kelvin, in which reverse saturation current is equal to 10 raised power negative 14 amperes, and theta is equal to 1 at bias voltage of 0.70 volts.
So all these values given appear in this equation. And then there is something we are taught here. We will assume that, oh yes, sorry, we are given eta equals to 1. So when we substitute in the Shockley equation, I told you this is known as Shockley equation, we are given VA, that is the biasing voltage, is 0.7, and eta is 1. The thermal voltage we obtained in another example is 26 times 10 raised to power negative 3. So when we substitute all these values, this is how it looks like, yeah? 0.7 divided by 0.026. When we get this 0.26 is the thermal voltage for a diode made from silicon. Okay. So the current is 4.93 milliampere. So this equation, the Shockley equation, if I can see it again, it gives us the diode current when we know the applied voltage or the biasing voltage. So we can plot a graph of current versus the applied voltage. And this diode behaves, it does not behave like a resistor. If you, I think in school you were taught that Ohm's law tells you the voltage applied across a resistor is directly proportional to the current. That relationship will produce a straight line because a resistor is a device we say a resistor is a linear device. A diode is non-linear, and I think that question was also there in the cut which you did yesterday, and it is called non-linear because you can see this curve for current versus voltage for a diode is not a straight line. There is a part which is curved and there is a part which is straight. So this is what happens. If I take you, let me just take you here. Let me take you back here. When we have the PN junction forward biased, when we have the PN junction forward biased, we have a very narrow depletion layer, but we still must overcome the barrier potential so we must create sufficient voltage, this biasing voltage, to be able to force us to cross the barrier, to cross the depletion layer. Likewise, that same voltage is able to make electrons cross the depletion region. So that is why when we start increasing the voltage across the PN junction, initially there is very little current which flows, but eventually we must overcome the barrier potential for current to flow. So that's why you see this. Let me get back to this graph. Look at this graph. So here, the current is very small as we increase voltage from 0 to a certain value. So current is very, very small. Now, what is happening here? You are now forcing current to cross across the depletion region. And when you exceed a voltage, for example, for silicon 0.7, you will get very high current for small change in voltage. So this region is when the diode is forward biased. I don't know whether you understand. And this curve is actually a product of this equation, which we call Shockley equation. Anybody with a question? So this curve, we call it, there's a name we give it, characteristic curve. So it is showing current versus voltage. That's why we are calling it a diode's IV curve. And diode's IV characteristic curve. Now the voltage, the current is very small, so that's why it is measured in milliampere. The voltage is measured in volts. And one thing to note that for germanium, the barrier potential is 0.3. For silicon is 0.7. Actually, in one of the examples which we did, we obtained the barrier potential to be 0.75 for silicon. So there's another name for this where the curve is turning to be a straight line. We call it this, we call this point knee. It looks like the knee, but this is where the diode is fully now conducting current. And for a small change in voltage, we get very high current passing through it. So the diode, we can say it's switched on at the knee voltage. Now the other side of this curve, which again is the diode IV characteristic curve, when the diode is reverse biased. This is how it looks like. Reverse biased will give us very, very small current. Look at the current axis for reverse bias. It is measured in microamperes compared to the current when the P junction is forward biased. Is measured in milliampere. So this current measured in microampere is very, very small. So what is happening? It is telling us as you increase the biasing voltage in the negative direction, you get very small current. Why? Because the diode is reverse biased. So there is very small current in micro means a millionth. But at some point, at a point here, which we call breakdown voltage, the the current improves suddenly. For a very small increase in voltage, current increases sharply. Now we say this at this point, the PN junction breaks down, and that's why we call this as reverse breakdown voltage. Let me check. I think there is a student who may be asking for something. If somebody has posted a question, I see questions here. Somebody answered something, said acceptor. Ireri said whatever this one means. Please don't write things which have no meaning to us. Now, one guy is asking, how do you obtain thermal voltage? One guy, is your question answered? Is your question answered?
Yes.
Okay. So let's continue in our presentation. So we are showing the variation of current with voltage when the diode is forward biased and when it is reverse biased. When it is forward biased, it conducts current very well, but you must overcome the barrier potential for the diode to start conducting. Now for the reverse bias, it allows very, very small current to pass through. And if you continue increasing the barrier potential, the depletion layer is so large that the PN junction is destroyed. And we call this voltage at which the diode breaks down. We call it reverse breakdown voltage. I hope we understand that. Then here we are showing an application of a diode in what we call a rectifier. A rectifier is a device which makes current flow in the same direction. Now, if you see here, we have a transformer. At least you understand this is symbol for transformer, and the transformer works with alternating current, AC. So this diode is connected, a single diode is connected there, and there's a load there where current is passing through. So this AC voltage, at some point it is positive and some point is negative. So we say there is reversal of direction of current. Current in positive direction, current in negative direction. So when this is positive, the diode will be forward biased. So it allows current to pass through. When it is connected to negative, no current flows. You can see here, no current will flow. Then the next one is positive, current flows. Now, if you want to ask a question, you can ask, because when I am doing a presentation, I cannot see there. Unless I escape from here, I cannot see what is in the chat. If there is a question which you feel I should answer, please just say you want to ask a question. So we are showing that a diode, a single diode, will only conduct one half of the alternating voltage. So this is not transmitted, this is transmitted. Therefore, we have, we call this one as half wave. We have only allowed this portion of the current to flow. This we did not allow, this we allow, this we don't allow. So we call this a half wave rectifier. And the current, you can see here, the current is positive, positive. And we say it is flowing in the same direction. You can see current flowing in the same direction through the resistor, but in the transformer, it is changing direction. So here we have AC input, we get DC output. Therefore, a rectifier changes from AC to DC. And a practical rectifier is like what you use in when you are charging your phone. Your phone does not use alternating current. So when you put your plug on a AC socket, there must be inside that charger, what you call charger for a phone, it has a transformer which steps down from 240 to 5 volts. And then you have a rectifier which makes that current DC from AC to DC. I don't know whether we understand. You, Okoth, you are following this?
Yeah.
Okay. Did you get notes for this rectifier? Or you did not check?
Not checked yet.
I think I did send. The slide which was numbered is number 6.
Oh, yeah, it's there.
Oh, yes. Okay. So let me just check how many are still with us. So please go through the rest of that slide so that we understand how can we produce full wave. Here we are only showing how we produce half the wave using a single diode. Now, there is a reason why we connect a capacitor is try to smooth this current, which is maximum, then it comes to zero to maximum. So when you connect a capacitor, when it is charged, when this is reducing, the capacitor will discharge like that until we come to the positive parts again when the capacitor will start charging. So in other words, we use the capacitor to smooth the this voltage. So the full wave rectifier consists of, for example, 2 diodes or 4 diodes. So we call this one full wave rectifier. And I want to leave it to you to see, are you able to explain how a full wave rectifier operates? The input to that rectifier is an alternating voltage and the output is DC voltage. But now you can see the full wave has been allowed to pass. For a single diode, we only allow one half of the voltage to pass through. So that's why we call it full wave. And we can use 2 diodes. We can also use, actually the most practical diode consists of 4 diodes. The most practical rectifier consists of four diodes, what we call bridge rectifier. Bridge rectifier. So I think we want to stop there. In the next class, which will be the face-to-face class, we will now show how the PN junction is applied to make what we call transistor. So next week we'll introduce the transistor. So let me stop there. and see whether there is anybody with a question. Is there a question? If you have no question and you want to log out, you can do so.
So are you in our office so that I come for the cut papers right now?
Yes,
Okay.
let's meet in the. You come to the office in math department, please.
Okay.
Okay. So students.